morning, everybody, and thank you very much for, first of all, organizing this conference. Sorry about my poor English. I'm going to say an awful lot of grammar mistakes, hoping that you will forgive me. I think it's a very good idea to have a conference like this one. It is informal. It is attended by people that really want to explore the possibility of future interstellar flight and something before that in the future that is precursor interstellar missions. As Les said, in Europe we have this set of conferences that have been going on for quite a few years. At Aosta, it's a small town in the Italian Alps, under the aegis of the IAA, the International Academy of Astronautics, of which I am a member. So what I'm going to tell you about here is basically the same presentation that I made in Orlando, Florida, just at the end of September, beginning of October, when, for the first time, I would say, in the history of the United States, both NASA and DARPA took, let me say, seriously the issue of future interstellar mission, and in particular the issue of precursor interstellar mission that would last, say, something like 100 years. So, as you certainly know, there was this, so as to say, call for new mission ideas. I'm using the European terms, but essentially that was the idea also in the United States. And so, in Orlando, Florida, there was this large conference attended by many tens of scientists, 100, 200 scientists or something like that. So here I am repeating the same presentation that I gave at Orlando in the destination session, or track as they said, chaired by Dr. Jill Tarter, who, as you know, is the leader of the SETI search for extraterrestrial intelligence at the SETI Institute in California. Okay, so let me come straight to the technical issues. Well, the point is that all of us have been dreaming about interstellar space missions. But before we attempt a real interstellar space mission that is covering huge distances, my suggestion is that we should take a closer look at the sphere around the Sun, located at 550 astronomical units, or in light time, something like a half light week, 3.17 light days. Because when we cross this sphere, whatever the direction of the crossing is, we can take advantage of the magnifying power provided by the gravitational field of the Sun, and that may lead to many unexpected discoveries. And also it is, as I would say later, crucial in order to keep the radio link across interstellar distances between the solar system and our own probe going out to the nearest stars, or even to the not so near stars. So the key point in my presentation is twofold. First of all, there is a benefit of the Sun as a gravitational lens that can provide enlarged magnified pictures of whatever is the object that we want to explore. And apart from that, the other advantage is in the telecommunication business that really, in my opinion, would fail if you do not take that into account, because the distances are so huge that the attenuation is so large, and so we don't keep the link anymore. So let me come straight to the point and show you what happens. Now, all this stems out of Einstein's theorem. So I'm not talking about exotic physics, nothing like that. This is absolute standard stuff in any general relativity course. What I'm describing here is simply a result of the so-called Schwarzschild solution. I know that in America someone says Schwarzschild or something like that. I am from Europe, as he was German, so I am saying Schwarzschild solution. But anyway, that is the simplest and actually most important solution in many regards. The idea is that Schwarzschild in 1916 was able to find out the gravitational field of the Sun, as well as of any spherical stars, of course, in exact terms. So there is no approximation in the equation. And the idea is that if you have a source of radio waves at infinity in this direction on your left, they could be radio waves of whatever kind. So it could be a radio galaxy, it could be a quasar, it could be a star, it could be an extraterrestrial civilization sending signal. It doesn't matter. All of them, when they arrive in the proximity of the sun, the trajectory is bent by the gravitational field of the sun. Now this is no new effect, because in Newtonian theory you can do the same calculation. But the novelty is in the amount of the bend, meaning that if you do the calculation in Newtonian theory, you find the same equation that Einstein found, but with a factor of 2 here, rather than a factor of 4. So there is a huge difference in between Newtonian gravity and Einsteinian gravity. Now, obviously, Einsteinian gravity is more faithful to reality than Newtonian gravity, as we all know. So the conclusion is that we should be grateful to Einstein, because he proved that the bending is twice as much as Newton said, foreseen. And so this means that we have only to go to half distance to find the focal sphere rather than the full distance. So we only have to go to 550 U rather than going to 1,000 U. And this, of course, is an advantage from the point of view of space missions. Now, the proof is absolutely trivial. You just consider that diagram. This is the minimal focal sphere, that is the focal sphere around the sun that is obtained by radio waves grazing the surface of the sun. And you clearly find out this angle, which is the same as this angle, by dividing the radius of the sun over the minimal focal distance. So, of course, you replace the tangent by the angle, because the angle itself is extremely small. So you have the first equation. Then you match that equation with Einstein's equation, which is this one, with the factor 4, and not 2, as Newton said. And you eliminate the angle, just trivial steps, and you find this bit. This is the most important equation of all. It's so trivial, but so important. Let me point out some properties of this equation. First of all, there is a constant factor, c squared over 4g. Okay, that depends on the gravity and on the speed of light. But the really important point is that, apart from that, there are two quantities playing in the game. The size of the star, in this case the radius of the sun squared, over the mass of the sun. And this is true, of course, not only for the sun and for all stars, but for all masses. So it is true also for the planets, meaning that each planet in the solar system does have its own gravitational sphere, focal gravitational sphere. Of course, the numbers are different, but it does exist. It's not zero. So, as I said, for the sun, the minimal focal distance that we must reach is actually 548.230 U, which is something like 550, which is half a light week. Or, if you prefer to compute in terms of Sun to Pluto distance, is practically 14 times the distance of Pluto. Now, when I first presented all these things, I actually submitted a proposal to the European Space Agency for a preliminary study of this mission in the year 2000. And as you can easily imagine, they turned down my proposal because this was regarded as too far-sighted. But nevertheless, when I proposed that, they were saying, oh, this is too much far away, you cannot consider anything like that. But in reality, this is not really the case, because the Voyagers have already reached 1/5 of such things. And the Voyagers were not launched at all for this thing. They were launched for other purposes. So my opinion is that bright people, as in this audience, can certainly devise propulsion techniques to reach the gravitational spheres and beyond in a comparatively speaking short time. I would say a few decades or even much less, a few years. Okay, now let's go over for a moment to the gravitational spheres of the planets. So once again, I said that this is the equation, so we just replace the sun with any object, whatever the mass and the radius is, and you replace the numbers for all planets, and you come up with this table. So let me show you what is in this table. Now, first of all, the first line, this line, is the so-called naked sun. Naked means that we are not taking into account the corona of the sun. So we are just considering the sun as if it was a perfect spherical ball, and we are just taking into account gravity, nothing else, no plasma effect, nothing. So for the naked sun, as I said, this is the minimal Fokker sphere, 450. But if you want to take into account the corona, as of course you have to, then my suggestion is that we should go up to 1,000 AU. That is twice as much. Now, once again, this is not something impossible, because the jet propulsion laboratory in the 1980s, there was a study funded by discretionary funds of the director of it, and led by the engineers, that was what exactly 1,000 astronomical units. So they wanted to get there. Now, if you let me be frank, the funny point about that is that they wanted to get there, but they did not know that halfway there was the sphere of the sun. And if you ask me, how is that possible? Very easy. Because there are different compartments of scientists, let me use these terms, and many scientists don't know each other. So at that time, the good experts of JPL did not know the gravitational scientists that had done all this in the field of general relativity. They did not know each other. So they were suggesting to go there, but for other reasons. For instance, the parallaxes of stars. Good. So let's go ahead and go to the next slide. The next line, of course, is the next mass in the solar system. So it is Jupiter. And this is the distance. And then you go on. Now let me show you a picture that shows you really what the situation is. Now this is a faithful picture. There is no stretching or compressing or nothing. This is the situation as it really is with the true reference. So the orange very small circle or sphere is of course the naked sun, 550. The blue one is the coronal sun, that is 1,000. Then the green one is Jupiter. And then the next is Neptune. If you are surprised, the answer is, well, it is like that because of the key quantities in the game, that is the radius square of the mass. Okay. So after Neptune, Saturn comes, and it is here. And surprisingly enough, after Saturn, the Earth comes. Now, when I first did this calculation, I was really surprised. What convenient, you know, that our small little Earth is next after Saturn. But actually, it is like that because the Earth is small, but it is very dense. It is actually one of the densest, if not the densest, body in the solar system. So this is what really matters in the game, not the size alone or the mass alone. And then you have other bodies, of course. So for instance, Uranus, even if it is bigger than the Earth, it comes after that, and then Venus and so on. So, what am I saying about all this? I am saying that whatever direction you take in the sky to leave the solar system and to reach the near star, you will have to cross all those spheres. And so since you have to cross them anyway, please take advantage of those. That is, put on the spacecraft detectors, and then we have to specify what that means. I think of telescopes, of course, but also radio antenna, whatever. So that, as long as our spacecraft gets out of the solar system, we get magnified images of what is on the other side with respect to the lens involved. Okay? Now, there is even one more advantage. Of course, the reference frame for this mission is the center of the sun. But when you go out, if you look at the gravitational lenses of the planets, of course the planets move around the sun. So you have a moving gravitational lens during your mission that gives you even much more details about the sky, because it covers a whole belt of the sky, you see. So there is plenty to learn about this. And I just would like to point this out, because whatever interstellar mission you have to plan, this will come as a bonanza, a bonus. We have to use that, not just to leave it unused. Okay, now I'm going over to some technical more details, and I don't want to go over my time, even if I...
Actually have more time than the others.
Thank you, thank you. So anyway, let me just give you some technical detail. Now, I spoke about the focusing power of the sun and of any body, actually, as a gravitational lens. But what does that mean in terms of gain? Now, here we have two different meanings of the word gain. Now, in classical electromagnetic theory, all engineers know what the gain of an antenna is. But here, we are talking about gravitational lensing, so it's a different gain. Although, finally, we match them in order to have the overall gain of the system. So, the gain of a star can be proven, but this is not an easy theory. That it is 4 pi square of the Schwarzschild radius, the gravitational radius, over lambda, which is the wavelength on which you are observing. So in terms of masses and so on, this is the result. So this is the gain of a star. And let me also point out what is the off-axis gain. Meaning, so far I have been considering the best possible gain, that is when you are on line along the straight line. But of course, if you move away from the straight line, you have a decrease in the intensity in the gain. And this is the equation giving you that. You have a Bessel function, or cylinder function of order 0 square times this stuff. So this is the equation for the attenuation when you are off-axis. And of course, I would suggest that on board the spacecraft we put some feedback system so that if, for any reason, the spacecraft gets out of the straight line, then immediately the feedback acts, and so it brings back so that we can keep the alignment at any time. Okay, now, as I said, there are two different gains in the game, because we have two different bodies in the mission. We have the sun, of course, but we also have the spacecraft antenna, which is up to us. So the conclusion is that the overall gain is obtained by multiplying the two. If you ask me why do you multiply, I will show you in a moment. So please just take it for granted right now. And in 5 minutes I will show you why it is multiplied. So in conclusion, the overall gain is really going to be big. This is the key point. And of course, if you have a larger antenna on the spacer, the better it is. This is the book that I wrote. Les was kind enough to bring here a copy of my book. I think this is his copy. I did not have space to put it in my case, I'm sorry. But anyway, you can find it on the web. And this is a technical book devoted to this space mission. Okay, so this I already said. It's a moving magnifying lenses. And now let me go over to the question of the radio link, because this has to be proven, in my opinion, in detail, although it is absolutely well-known material. But it's useful to know, because now we are going to make the next step. That is, not only to consider our own star as a magnifying lens, but also to consider other nearby stars as magnifying lenses. So let me please just review the basic equation of the booster. Now, the radio link is given by this equation. You have the received power, PR, is given by the transmitted power times the gain of the transmitter times the gain of the receiver over 4 pi square times the distance square, obviously, over the wavelength square. This is a trivial formula. It can be easily proved. It's proven in my papers, and I can give you the references and so on. This is absolutely ordinary stuff. So, when you do that, then you have to do one more point in the chain of reason. We have so far only considered the physics, but not the telecommunications. Now we are going to consider the telecommunications. Now, when you consider a telecommunication system with spacecraft and so on, you need a thing which is called the bit error rate. What is that? Well, the name tells you all. It is the probability that, or the frequency if you want, that if the transmitter is sending a 1, you get a 0, or the other way around. And this is because in between the transmitter and you, there is noise, space, but with noise inside. The space is not empty. There is noise of all kinds of radio waves, types produced by stars, whatever events in the universe, and so on. Okay? So the bit error rate is a probabilistic measure telling you how lucky you are to get the right signal or how unlucky you are not to get. And it can be proven mathematically if you just look at the Wikipedia site, it gives you the proof. That this thing, for a probe at distance d, transmitting at frequency nu, and with the power p sub t, the transmitter power, this thing is given by the complementary error function, which is an integral of the Gaussian probability distribution. So the complementary error function of the square root of these things. Now, this n sub 0 is essentially the noise temperature of empty space. So this is the critical point, meaning that space is empty, but there is noise, as I say. And you find it by multiplying the temperature of empty space times the Boltzmann's constant. This is traditional stuff in thermodynamics. Now here you have another thing which is called, which is the received power over the bit rate of the transmitter. That's all. So this thing is called bit error rate, and then we go over to a practical example. Now consider a probe of ours that is leaving the solar system and is getting out, for instance, the direction of Alpha Centauri. Now clearly we have to keep the link. It's not just a matter of proportion. I know that the vast majority of scientists dealing with interstellar flight think of propulsion, and they are absolutely right, because this is the #1 priority. But it's not the only priority. Keeping the link is equally important. So the question at this point is, are the deep space networks antenna of NASA sufficient to keep the link up to what distance? Question. And I have to say that I am not so much optimistic, because even if they keep the link wonderfully within the solar system, when you get out, I would say even just a few times of the size of the solar system, then the attenuation is such that the link becomes difficult. This graph shows you that on the horizontal axis you have the distances from the sun in light years. On the vertical axis you have the bit error rate, which, as I said, is 0, meaning that you have perfect telecommunication, and is 0.5, that is 1/2, if you are in the worst case where the probability of getting 1 instead of 0 is 1/2, and the other way around. So you mix up practically the whole message. Okay? Now the point is that if you use just the deep space network antenna, and just for the sake of an example, I use the Ka band, which is 32 gigahertz. And if you ask me why did you use that, is because I was involved in the study of the Cassini mission. I was working at the Spatio. Many of you may know that the big antenna on the Cassini space was built by my company, Alenia Spazio. So I have some knowledge about all this, and the highest frequency for the Cassini mission is Ka band, 32 gigahertz. So this is why I use that, right? So if you use that, you see that already at very small distances, the bit error rate starts jumping out and reaches the dreadful value of half, that is mixing up completely the story, already at 0.1 light years. This is no good. And I know that many engineers, I've been talking about that with people I know they say, oh, we can use laser to do it. True. But why do you use laser? First of all, the pointing might be size, but then apart from this, there is a difficulty in this, the attenuation is huge. So my suggestion is to solve the problem from scratch by using the sun as a gravitational lens to keep the link. And this gives you the red curves, which is practically 0 at 0.1 or much more, much higher distances. In other words, before sending the real interstellar spacecraft, we have to send a relay satellite in the opposite direction of the sky to the minimal focal distance of the sun, say 550, say 1,000 AU, and that will help to keep the link with the real probe going away on the other side. Incidentally, I have to say that I'm in touch with the group of Icarus study, and I'm very pleased that the young guy from the Icarus study, Pat Gallia, already went beyond the work I did. So Pat Gallia essentially found a system to keep the alignment perfect by putting 4 relay satellites into to orbit around the Sun in a plane perpendicular to the exit direction at the distance of 7. So his paper was just published 1 or 2 months ago in the Journal of the British Interplanetary Society. If you go there, you'll find all the details. And I'm glad that someone is working furthermore than I could possibly do. So let's go ahead and let's increase the distance, because now we want to see up to which distance this trick works. It cannot work forever. It will stop working. So now again, on the horizontal axis you have distances in light years, so we are going up to 10 light years, much beyond Alpha Centauri. Alpha Centauri is around here. And of course, without the Sun, this is already completely crazy, right? We cannot get Jupiter away from point 2 or point 5. But only at, say, 8 light years does even the gravitational lens of the Sun fails or start failing to keep in the link, okay? And just keep going. So once again, this is the distance in light years, and you see that practically beyond 10 light years, even the Sun doesn't have much more. And finally, at 100 light years, it is 0.4, so it is practically complete mismatch in the okay? So this is the suggestion. 40 light years is quite a bit compared to the Sun, certainly not compared to the galaxy. So let's take a further step from these, please. Now, the further steps implies a different story. Let me explain it by words before I give you the graphs. It is clear that in this situation, only the Sun is helping us. But suppose for a moment that we already sent a probe to Alpha Centauri. And then the question is, okay, what are we going to do with that? My suggestion is put the probe on the other side of Alpha Centauri A, which is the biggest star out of the 3 stars, in the direction opposite to the Sun, and put another probe at the focal distance of the Sun, so that in conclusion you have a so-called radio bridge, where you have 2 stars, the Sun and Alpha Centauri A, and 2 relay satellites on the opposite side. So altogether you must keep 4 points aligned. But of course this should be not so difficult, because you are free to move the 2 relay satellites. So you just keep the control system well enough to keep the straight line, okay? So, at this point, we have made a step ahead, because we are now going from a 1-star gravitational lensing system to a 2-star gravitational lensing system. And so, in the equation giving you the gain, of course the gain of the next star is reducing the powers in the gain much more, because of the second gain, okay? So this is the basic framework. And now let me show you the graphs. For instance, these are the data of Alpha Centauri A as a lens and so on and so forth. Of course, the Schwarzschild radius is different because the star is different. These are the data, nothing. But this is the new point. You just consider the previous plots, but now you change one thing. Since the distance between the Sun and Alpha Centauri, of course, does not change, on the horizontal axis, you do not put the distance anymore, because the distance is fixed. So this, mathematically speaking, gives you the freedom of changing the independent variable. And now the independent variable becomes the power requested to keep the link in between these 2 stars, okay? So this is the new graph. On the horizontal axis you have the powers in watts. 10 to the minus 10, minus 9, and so on. Of course, this is a logarithmic scale. And it depends on how much power you put into the system, but essentially this tells you how much power you have to put in order to keep the link. And so you see that in the beginning you cannot keep the link if the power is too low, because the noise in the space is too much, essentially. But when you reach a certain point, you have an E, an inflection point here. And then you go down and finally you reach 0. So for instance, for the Alpha Centauri A, with the power of 10 to the minus 4 watts, which is really modest power, you can keep the link. But this is, of course, thanks to the gravitational lenses, the 2 gravitational lenses of the stars in the gate. So, conclusion, we can certainly call Alpha Centauri with a cell phone, but only if we use both stars as gravitational lenses. And of course, we must wait 4.3 years for the message to get there and to come back. This is today's physics, not tomorrow's physics. I'm not talking about wormholes or whatever. Okay, now, let me go over to the next star, Barnard star. Same story, but with the difference that Barnard star, unfortunately, is a small red star, and as you know. So you do the same calculation, and Barnard star's curve is this one. So you see that the same trick for Barnard star is less efficient than for Alpha Centauri A, clearly because Barnard star is a smaller star. That's all. Let's go on. This is Sirius. Wow, Sirius is a bright star, but it also is 8 light years away. So the blue curve is Sirius. And so you see that this is nearly as good as Alpha Centauri A, and certainly worse than Barnard star. So, once again, what matters in the game are the masses and the sizes of the thing, nothing else. So, at this point we have discovered an important thing, that radio bridges can be built among any couple of stars in the galaxy. So, we humans just came to understand this now, I would say. But then the next question, going over to SETI, of course, is, well, if we discovered that now, maybe there are some more intelligent guys somewhere else in the galaxy who understood the same story already a long time ago. So, regarding this not as science fiction, but as a physical reality, as it is, because this is just pure physics, no spatial trick of any kind. There might be a galactic internet at work in this galaxy right now. But we don't know about that. And we don't know about that because we never reached the minimal focal distance of our own star, which is the Sun. So the bottom line of the story is that this mission to 500 LU or 1,000 LU or further out is absolutely necessary. Because if we don't do it, we will never get in touch with aliens if a galactic internet exists. Now, you may object, yes, but you have to select the direction of the exit. Absolutely correct. And I would like to suggest one direction, that is the direction opposite to the galactic center, the center of the galaxy, where we know, and we have discovered just in the last 20, 30 years, that there is a huge black hole called SGR A star, whose mass is about 4 million solar masses. Now, let me just tell you by words what the conclusion is, okay? The galactic center is not a point like anyone else in the galaxy. It is the most important, is the capital of the galaxy, in plain terms. Because, and here I anticipate the paper of mine that is coming out on Acta Synoptica just in a short time. Check the proof already. Because if you redo once again the full story, not for stars, but for black holes located at the center of galaxies, then you discover an unbelievable thing. That is the radio bridge between black holes, this is an overview, never presented that, between black holes of nearby galaxy, for instance, our own black hole with Andromeda black hole, performs even better, thank you, even better than the Sun Alpha Centauri A bridge. Now this is of course unexpected. As long as you don't do the calculation, you cannot even imagine that. So this brings one more point in the story. True, we are not at the center of the galaxy. We are not living in the capital. We are living in the far outskirts. Really unimportant people. I'm sorry about that. But there might be someone else living at the center of the galaxy that is using the galactic black hole for communication with other galaxies. And we are completely cut off from that because we didn't even learn to use our own star as a gravitational lens. So the conclusion of the story is that preparing and planning, and of course limited funding, but funding, the focal space mission to 550 AU is absolutely necessary for whatever kind of human expansion beyond the solar system we would like to do in the future. Thank you very much.
We do have about 5 minutes or so for questions, so I'll let you point to who you'd like to take.
Yes. Prego.
If the aliens are using black holes, where do they put their relay stations? And is there something we would look for if we wanted to just see or know that their relay stations exist? Not so much to go there, but are there things we should be looking for to see if other people's relay stations exist?
Absolutely.
These signatures we
Well, this is a difficult question because, unfortunately, the sphere at 550 U is huge. But it is not impossible, I would say, because if they use, let me say, traditional radio antennas, we all know that there are side lobes. So even if a relay spacecraft is there and is looking in another direction, not in our own direction, with very good receivers on Earth, we might be able to intercept a side lobe of these antennas. So that would get us rid of the direction question, right? I don't know if I answered your question, but this is my answer. Thank you. Yes.
The audience might that Frank Tipler, arguing from the point of view of both physics and theology and philosophy, argues that way down the line, intelligence will begin to inhabit the event horizons of these black holes, including the one at the center of the universe. So it certainly is not impossible that we could look there right now. The second thing, you might be aware, and the audience might, that Carl Sagan and Newman, I forget Newman's first name, shortly before Carl's death in 1995, published a very interesting paper on interstellar scintillation, which is directly relevant to what we're talking about here. One of the protocols in SETI says that for it really to be an interstellar transmission from ET, it must be repeatable. So far, nothing repeatable has been detected. On the other hand, when Sagan wrote this, there were more than 30 very nice wow signals, as they're called, which were significant but did not repeat. What Sagan and Newman thought is maybe some object had come between us and an alien transmitter of low power, and of course we had gravitational lensing. So the fact that you've added numbers to this is very significant.
Thank you. Yes.
Has there been any work done on using the Earth as a gravitational lens for observations locally?
Well, thank you for that, Bob, because this is a really good question. My answer is, to my knowledge, no. So when I published this paper that I showed with the gravitational sphere of the Earth, first of all, I was surprised that it is lying in between the other big planets' gravitational sphere. This is the first point. The second point, I suggested very briefly, it was published in Art Astronautica just 1 year ago, that we know, of course, the atmosphere of the Earth better than the atmosphere of any other planet. So when interstellar probe, precursor interstellar probe like the Icarus project is planned, my suggestion is that we should put aboard some kind of device. I am not an engineer, so this is your job, gentlemen and ladies. This is beyond my reach. But we should put some kind of device so that when it finally reaches the gravitational sphere of the Earth, that we know about better than anything else, we could use it to magnify whatever lies on the other direction. Also taking into advantage that the Earth moves, so it is a sweeping thing. Now, let me please tell you something more about that, because this is an important issue. In the cover picture of my book, I don't know if you can see it here and so on. Anyway, I imagine the Fokker spacecraft as follows. It's not just one antenna. One antenna is the minimum, but that gives you a very small field of view on the other side. My understanding of the system is that there are two antennas. Can you see these two things, two circles already, tied to each other by a tethered system. So basically the idea is that if the spacecraft is moving away, that is the sun, the spacecraft is moving away this way, the spacecraft proper releases a tether on two sides, and these two antennas that are tied to each other on the tether describe Archimedean spirals as long as the tether is released, okay? So they cover a much larger field of view on the other side than just a single antenna. And also you have two antennas, so the collecting area is double, so you have better sensitivity. Now this is absolutely indispensable for the first Fokker mission that I mentioned, that is the Fokker mission intended to watch the gravitational lens, the black hole at the center of the galaxy. Actually, Lester and I were talking about that already years ago. It is easy to prove that a tether on something like 2 kilometers, or say 10 kilometers at best, gives you a wonderful picture of the black hole at the center of the galaxy and of the stars orbiting around that thing. So, from the technological point of view, a tether like this is perfectly feasible. I mean, let me frankly say that I work at Alenia Spazio. We did build the tether satellite of historical memory. And that was deployed to 18 kilometers. So certainly this can be done. So this, once again, is a feasible thing, not something for the future.
Probably time for one more question, and we need to move on.
Well, this is all for electromagnetic radiation. Would it be of any advantage to put the detector there for gravitational waves?
Yes, of course. But as you know, a detector for gravitational waves may be not a small thing. I put it philosophically or euphemistically if you want. But so, you see, the point is that, of course, we must have a trade-off when we are planning a realistic space mission. So, if I go to NASA and propose to put a gravitational wave detector on, the masses involved, in my opinion, are so big, and this is no good, honestly. So this is why I confine the whole book to electromagnetic radiation only. Incidentally, let me please mention, just as a final point, an idea that Greg and I had already many years ago. Consider solar sailing, as Greg will be described, okay? Consider a large solar sail going away from the sun. Now, when that reaches, say, the distance of Jupiter or Saturn, of course it is useless because the radiation impinging on the sail at that distance is practically zero. But the point is to design such a spatial sail that it is sailed only on one side. So you have the sail, as long as you get away from the sun, up to Jupiter or Saturn. But when you get there, you turn the sail by an angle of 180 degrees, and the other side becomes an antenna. So for you engineers, please think about that. You know, the matter is to design a sail which is sail on one side and a big antenna on the other one. This would increase the gain enormously because, of course, the size of the sail is enormous too, and would give us even better pictures and telecommunication with the space.
Very good. Thank you, Claude.
Thank you very much.